to learn how to code the steepest descent method, and assuming that you guys have already followed the algorithm that exists out there. So we're just going to start with a fresh Jupyter notebook, and the first thing we're going to do is we're going to populate the libraries we need. As usual, we're just going to go to any other things we have done before, and we're going to click on it and see what imports we need, and we're just going to import some of this kind of stuff over here, and I'm going to just click it into here. We probably would not need pickle here, so that's basically file sharing, file opening things, and I'm just going to use whatever I need from Torch over here. And that will be our first step before we do anything, just to prepare all the libraries we need in order to code something. And again, this cell runs and everything seems to be fine in here. That's our first part. Done that, we basically want to start thinking about writing our code. And what I'm going to do is I'm going to divide this thing into two steps. The first thing, I'm just going to write all the codes in comments. So I'm just going to write the skeleton of the algorithm, and then I'm going to start replacing or adding above the comments the lines of code that's supposed to do this. So what we're going to have is a function that is basically a steepest descent function. And the steepest descent function, to remind you, we have to think about what it takes. So steepest descent will take in some kind of a function, f function, which I'm going to call func, and it's going to also take an initial point, which we call theta 0 in this case, and maybe we'll take other arguments. We'll figure it out a little bit later, something like number of iterations, and then maybe also some what we call the parameter that control the step length, so we'll call it mu, and maybe I forgot something. We'll figure it out as we go along. And what it does something very, very simple. So we basically initialize to have theta to be equal to theta 0, so theta is equal to theta 0, and then we go for I in range of number of iteration. What we would do is we would just go ahead and say that compute the function and its gradient, and then we can just go ahead and say update theta to be theta minus the gradient of the function times basically this parameter mu times this. That's basically all the algorithm is, and what we want to return is basically the parameter theta. And that's basically the algorithm. That's basically it. We may want to do some printing, want to do other things. So we're going to write this like that right now. And in the next phase, we're going to start kind of doing step by step this kind of piece and fill in these things as we go along. To start the third step, and the third step is actually starting to replace real pieces of code instead of this very schematic kind of algorithm, and thinking about really small details. So let's start with the simple stuff. Simple stuff, if we have a function here, we can go ahead and just say that what we want to do is want to write it as a def, and it's going to be sd for steepest descent. Function is going to be func, so that's basically the function name. Theta 0 is still theta 0, that's going to be the vector of parameters. We just do the same thing as num iter over here, and mu for the parameter that we want to do the step length. And that's relatively simple. We go, I guess, from here, and we have to indent, so the usual thing. So then theta is equal to theta 0, that's fine. And now we kind of do this thing as we wing it, and we start doing it this way. We start taking the for loop. So for I in range number of iterations, I guess it should be num iter over here. So the parameters are going to be the same. And what we have to do now first is compute the function. So the first step, compute the function. And then I'm going to say the gradient I'm going to take separately. So what I'm going to write is I'm going to write f is equal to, I'm assuming that I can do this kind of thing. This is func of basically theta. I'm assuming that this can be done, and this is something that will give me back an answer to the whole thing, and later on we'll see how we actually implement this thing. After I've done, and by the way, this has to be indented, otherwise things will never work in here, so that's important. Next things after that is to compute the gradient of the whole thing. So in that case, I just have to make sure that I look at basically f dot, so maybe I should write it as a comment here, just update compute gradients. So compute gradients, and the gradients are going to be f dot backward. And that gives me back the gradient, and remember that the gradient are stored inside theta. So I can basically write right now that grad f is going to be equal to theta. What we're going to be doing is we're going to now take the gradient of this thing. So that's basically the gradient is stored at theta dot grad, and that's the gradient of theta. Now, in principle, we need to just go to do the update. So let me just write here. This is the updation of the whole thing, and now we need to do the upgrade. So the way to do the upgrade looks like the first thing you would think is to say, okay, let's just do something very simple here. We're going to just write something like, okay, so theta minus equal to theta mu times grad f. And that seems not to work, but that would be a mistake. The main problem is that remember that the theta is going to be a parameter that we trace. So we trace everything that happens to theta, and we're going to differentiate everything and all the operations that happen to theta. If we do that, then we are going to differentiate through that thing later on in the next iteration, and that is going to be a problem. So this approach, this particular step, we want to make sure we're not actually using the gradients here. The way to do this is to write with torch dot no underscore grad, and that's basically giving you something that will require not to compute the gradient, and then you would do this in the line below, and that will do the update, which I'm going to write over here. So we're going to say that we're updating this whole thing over here, and that's what's going to happen here. Now, the problem is that we have done this. We now still have something. We populated the gradient. So next time we're going to do the backward, we already have something stored inside the gradient. What we want to do is we want to make sure that the gradient is set to 0. Otherwise, the upgrade will just add consecutively to the whole thing. The way to do this is to do something very simple and to just write a theta dot grad dot fill underscore 0.0, which means we're just setting all the gradients to 0. That's basically it. We're basically done. And now we need to return something. So we're finishing over here. We're making sure that we are just in the same line of the for loop. And we say return theta. And that is it. The algorithm is done, and that's everything you need to in order to have the steepest descent algorithm. In the next thing, we'll see how we test it. We test the function we would like to actually code. One of the things that is worthwhile looking at is actually printing some things to the screen, because if we want to minimize something, we should be printing some things. So one of the things we can print at every iteration, for example, we can print the iteration number, and we can print the function and the norm of the gradient. That will at least help us knowing what is going on here. So what we're just going to do something is I'm going to just write print over here, and what we're going to print here is the function, and I'm going to do the torch dot norm of the gradient of the function. So I'm just looking at grad f, and to be honest, maybe it's nice to be also printing what is I over here, so we can just see what happens as we go along and see if we are actually decreasing the value of the function or not. That's the next thing to do. Before I go ahead and test this thing is just to make sure I have all the right syntax things. So I believe I'm missing some stuff over here, and I believe the no grad requires something over here. Let me see if this cell runs, and it runs, and that's fine. Okay, now we need to test it. So the way to test this kind of codes is to start with something very simple that we know the answer, but maybe not that trivial. So what I'm going to do is I'm going to start by thinking about a function that is a two-dimensional function, or maybe a little bit more, doesn't really matter, but it's a very simple function. So I'm going to define a function. First, I'm going to define a matrix A, which is going to be a torch dot run done, let's say 10 by 10, and to make sure it's positive definite, I'm going to write that A is equal to A dot transpose times A. So that's basically give me a matrix which is symmetric positive definite, and I'm going to define a function which I'm going to call it my fun, and what it would take, it would just take the parameters theta, and what it will return is a quadratic function which is going to be x dot transpose times open brackets here a times x. So sorry, x is not x, it's theta. So we're doing theta here and theta. And this function runs. Let's just see that it gives us some results. So if I take theta to be torch dot rand 10, and I write y is equal to my fun of theta, I should get some kind of function. I can do print y, and it should give me a value. That's hopefully it, and that's would be it. Now, this is a symmetric positive definite matrix, so the minimum, of course, is at 0. The function, the thing that minimizes it will be 0. Theta equal all 0 would minimize this expression. Anything else will be positive. So I know the solution, and in principle, I could use these kind of things in order to just test my function. Minimize this function that I just defined. I will want to use my code, but I have to remember that theta is not just a regular parameter anymore. It's a parameter that I need to be tracing. So I'm going to be writing now, redefining theta as basically torch dot random, in this case 10, but it's not just any random. It's something that requires a gradient. So for that thing, I can say requires, I'm going to make a mistake on this thing, underscore grad equal to true. So that means that I'm going to have a parameter here that requires a gradient, and that's going to give me a theta that is requiring not just the parameter, just the regular parameter, but it actually I'm tracing it to get the parameters. And now I can just call my code. So here's my steepest descent code, just copying it as is, and I'm just going to do this, go back to here, and I'm going to write it as maybe theta out is equal to SD. Now funcs change for my fun, and theta 0 becomes my theta I started with. Let's say we're doing only 10 iterations for a second, and mu, let's pick mu for 1e minus 2, and that's hopefully this runs. Oops, because I put a dot here, should not have a dot, and that runs. And we can see that the function actually becomes smaller at every point. It starts at 166, it gets to 2, again we should get all the way to 0. The gradient, the norm of the gradient starts at 128, it got all the way to 6, and I can run it again. And by the way, when I run it again, it can save the values from before, and you can see that it starts lower. And if I continue on to run it again, it will continue and run even smaller. So if I run it many iterations, I'm getting closer and closer to 0. And if I go into to do something like print theta out, we will see that print theta out. We see that the values are starting to get small and they're getting closer to 0, which is exactly what I wanted. So that is basically the first part of this video tutorial of how to use these kind of things to compute gradient. And the next part, we will actually do something a little bit more sophisticated that shows you what the power of this kind of technique to solve really complex problems that are not that simple to do otherwise.